You're watching the second half of a two-part series dealing with applications of systems of equations.
You're going to take 80 kilograms of molten alloy, so be careful. That molten alloy is 30% iron, 15% nickel. You want to change that so that it will contain 34% iron and 22% nickel. You want to increase the content of each. And you're going to do that by adding pure iron and pure nickel. And the question is, how much do you have to add? How much of each one? So you're going to add some iron to get the iron content up, and nickel to get the nickel content up. One of the key facts here is, are you going to have 80 kilograms when you're all done? No, you're going to have a little bit more than that, depending on how much nickel and iron you add. So take just a couple minutes and see what you can do with that. We'll work through it together in a minute. What two things are we told about that our equations are probably going to involve? What will our two equations be based on? The percentages of what? Iron and nickel. Okay? Here we've got two different components that we're adding, and we don't know what either one of them are. So one equation is going to involve getting the iron content up to where it should be. The other one is going to involve getting the nickel content up to where it should be. So one equation is going to involve iron, the other involve nickel. Okay, well, what two things are our unknowns? The amount of nickel to add and the amount of iron to add. So I'm not even going to give you a choice this time. We're going to call our unknowns N and I. N being nickel and I being iron. Okay, now let's write an equation that involves our iron content. Let's start out with that. How much iron do we have to begin with? How much iron have we got in our original mixture? 30% of 80. Okay, so the amount of iron from here plus the amount of iron from here plus the amount of iron from here has to be the amount of iron in the total. Okay, we know that this new mixture has got to be 34% iron and 22% nickel. So our iron content, from here we have 30% of 80. That's not the only place we're getting iron from. Where else are we getting iron from? Right here, 100% of I. So how would you write this? 100% of I is, I, 1.00 I, or just I. I'm going to write 1.00 I just to clarify that we're taking I. How much iron are we getting from the pure nickel? None, so we don't need to do anything there. There's no iron coming from this. So that's the iron that we originally had. We're adding 100% of the amount of iron we had. And how much do we want to end up with? We want to end up with 34%. 34% of what? That's the question. How much of this stuff are you going to have when you're done? 34% of your total. What's your total? Huh? Nope. 80 plus I plus N. So it's going to be 34% of the whole mixture. 80 plus I plus N. There you go. Well, once you get one equation, and if it makes sense, the other one just falls right into place. Different values, but the exact same principle. So what's our nickel content going to be? 0.15 times 80, 15% of the original 80 kilograms plus 100% of the pure nickel. And that's going to equal 22% of, again, the total. Now, we can clean that up and rewrite it as our first step. Just to save a little bit of time here, I'm just going to tell you how these simplify. First of all, the nickel content, 0.15 times 80, this is going to, when all is said and done, become negative 0.78 N plus 0.22 I equals negative 5.6. That's just saving a little bit of time on algebra so that we can do some more setup problems. The top one, once you go through and combine all those like terms and get them so that they're in the same order, Ni equals constant, you will end up with 0.34 N minus 0.66 I equals negative 3.2. Okay, so this is the system that we now want to solve. That's the original one. This just gets all the like terms combined and in the right order. Now, here you've got a choice again. You've got a system. What method would you choose to solve it? But we can take that top equation times 3 and add it to this bottom equation. Okay? I was just going to say, I think what I'm going to do, just because I do have 2 more problems that I want to work through with you, I'm just going to tell you how this works out. Okay, I'll trust that you could solve that system. If you do it, as it turns out, I equals 10 and N equals 10. What are we given for sig digs here? I forgot. Oh, we're given 2 sig digs all over the place, so we'll stick with that. 10 kilograms and 10 kilograms. Plane flies into the wind, travels 725 miles in 8 hours. That's into a headwind. So is that wind going to slow the plane down or speed it up? It's going to slow it down. It's flying into the wind. So then the plane turns around, flies back. The wind has not changed. Now the wind is going to speed the plane up. It takes only 6.25 hours. We want to find out what the speed of the wind is and what the plane's airspeed is. Same distance. Yep. So, miles. There's our airplane. It's going to fly 725 miles in 8 hours. The wind is blowing initially against it. Now, just to get a handle on this, to get the idea down, suppose this plane has a cruising speed of 400 kilometers per hour. 400 miles per hour, okay? 400 miles per hour. If there's a 50 mile per hour headwind, what is the plane's true speed? The plane wants to fly at 400, but there's a 50 mile per hour headwind, so the plane is going to travel 350. But on the way back, what kind of speed is the plane going to make? 450. Okay? It can return in 6.25 hours. Okay, so if this is just a hypothetical to help you understand the problem, but if the wind is 50 and the plane flies 400, On the way out, it's going to get slowed down. It's only going to fly at 350 miles per hour. But on the way back, the wind will be helping it, and it'll fly back at 450. So when the plane's flying into the wind, what do you do with these two speeds? You must subtract it. But when it's flying with the wind, you can add it on. If that makes sense, then you're in good shape. Now, the other fact that we need that we have used before is this fact, the fact that distance equals rate times time. Let's just make a note of that over here. Okay, let's assign some variables to our unknowns. What's the question asking? Wind speed and plane speed. So let's make the wind speed W and the plane speed P. Now, what two pieces of information are we given that are probably going to form our two equations? Well, we're told the times. That's good news. And we're told the distance. So we couldn't really write an equation with a distance because we already know what the distance is. And we couldn't really quite write an equation involving time because we already know what the times are. But what two separate cases does it give us? It tells us the trip out, and then it tells us the trip back. So we're gonna use the distances and the times to write an equation for the trip out. So let's write the distance equals rate times time equation for the trip out. Expand on that a little bit. To our destination. And from our destination. So to our destination, our distance, all we're going to do is take distance equals rate times time and fill it in for each case. Distance to 725, that doesn't change. That's equal to our rate. What will be our rate on the way to our destination? P minus W. P is the plane's rate, wind is the W's wind, W is the wind's rate. So our rate on the way out will be P minus W. The plane speed minus the wind speed. Times time, what's the time on the way out? 8 hours. There's one equation. From 725 equals P plus W. That's right, P plus W times 6.25. There's your two equations. We can simplify that just a little bit, rewrite those. The top one, to our destination, will become 725 equals 8P minus 8W. And the second one, returning from our destination, will become 725 equals 6.25P plus 6.25W. And there's our system. Gabe? It turns out that the plane speed is equal to 103.3 miles per hour. And the wind speed is 12.7 miles per hour. Okay, last one. Same thing here, but we're going to replace the wind with current and replace our airplane with a boat. Other than that, it's the same idea. You're going to hop in the Mississippi today when you get out of math class. Fire up your little Evinrude outboard, and you're going to head north. The river's going to flow at 2.3 miles per hour south. Now you're going to hop in the boat. And you're going to go upstream for 8.5 hours. Then you're going to turn around and you're going to go back to La Crosse, and it's going to take you 4.25 hours. And the question is, how far did you travel? How fast was the boat going? Very similar to the last one. It's very similar to the last one. We know that distance equals rate times time. What are the two things we're going to write our equations for? What two separate facts are we given? Well, our two unknowns are the speed of the boat. So let's let B equal the boat speed. And the other unknown that we want is the distance. All right. So we're given two separate facts. We're told about the trip up and we're told about the trip back. So let's do our setup almost exactly the same as the last one. Going upriver, we have what? What's our distance? D. We don't know. That's one of the things we want to find. So upriver, D itself is one of our unknowns. D is equal to, now what's our rate going to be? We want to know what the boat's speed is. That's relative to the water. But we want to know what the boat's speed is. But is the boat going to travel the same speed both ways? When it's going upriver, what have we got to do to account for the current? Take 2.3 miles per hour off because the current's pushing it back. So our rate going upriver will be B minus 2.3. That's our rate going up the river. And the time going up the river? 8.5. There's one equation. And then we've got the return trip. Our distance? Still don't know it. It's still D. Same distance. That's going to equal, now we're going downstream, so what is the current going to do to us? It's going to push us along, and our new rate going downstream is B plus 2.3. So that's our rate, and our time returning is 4.25. There's our setup. B and D are the two things that we want to know. All right? Now, what method would you use here? Now, there's only one good answer to answer this question. What method do you want to use to solve that? You could eliminate. Use substitution. The distance has got to be the same both ways, so make a substitution. This distance has got to equal that distance. Substitute this D into there, and so we get B minus 2.3 times 8.5 has got to equal D, but D is also equal to B plus 2.3 times 4.25. Okay, by substituting in, you have no D in there at all. And if you solve that, it turns out that B is equal to 6.9 miles per hour. Then we can go back and find D, and you'll find out that the distance was 39.1 miles. And we're done.